Good morning. I'm going to tell you today about the Enabling Technology Development and Demonstration Program. And this program lays the long-range technological foundation for a lot of the other activities that you'll see throughout the day. And it's also going to demonstrate some critical capabilities for exploration in the near term. I've been leading a study team for the past few months, coming up with some initial plans for this program. The team has involved some very smart people from throughout NASA. And we've recently started to engage the NASA centers through the budget process for next year. And we've assigned a lead for this program to Glenn Research Center. And Tammy Harrington is the lead at Glenn to continue development of the plans as we go forward. So I'd like to recognize Tammy. Tammy, could you stand up, please? Okay. So please feel free to ask questions you might have of me, of Tammy, and my study team members who are here today. Okay, so what I'd like to tell you about today are the objectives of this new program, our proposed implementation approach, how it relates to all the other technology programs, both within ESMD and in the new Office of the Chief Technologist. I'll describe the program structure, which involves near-term demonstration projects and longer-range foundational domains. Then I'll describe an initial set of demonstration projects that we've planned to begin next year and how that relates to the request for information that we issued on May 10th. And then I'll describe a little bit more about what each of the foundational domains involves and our notional acquisition strategy. So to begin, the objectives of the program are to develop, mature, and test enabling technologies for human exploration. And we have two parts to the program. We have near-term demonstration projects, which develop prototype systems and demonstrate those systems in a relevant environment. And then we hand those off to other exploration programs, such as the Flagship's Technology Demonstration Program or the Exploration Robotic Precursor Mission Program, or to other missions of opportunity, such as international and commercial missions. In parallel, we're developing long-range critical technologies to provide a key set of capabilities that we'll need for our future exploration missions. And as new, really innovative technologies that are potentially game changers are developed by the Office of Chief Technologist, we will provide the infusion path for those innovations to come into our exploration programs by focusing those cross-cutting technologies on more exploration-specific applications. We have this architecture team called the Human Exploration Framework Team that's developing plans for our future human missions. They're going to identify systems and operational concepts. So one of the objectives of this program is to build some of these proof-of-concept systems, test their feasibility in ground and field tests, and then provide an assessment of how feasible they are back to the architecture team to help inform their future studies. And a number of the technologies we're working on have terrestrial benefits. We're developing high-efficiency space power systems that could enable clean energy technology on the Earth. We're also working on recycling air and water and waste in our life support system project, which could help with protecting the environment. So those are our main objectives. In the process of implementing these objectives, we're going to use multiple venues and platforms. We may do tests in the laboratory, we may do tests in the field, in analog environments, we may do tests on the International Space Station or on sounding rockets or aircraft. So we're taking advantage of the full range of available platforms to do these demonstrations. We'd like to leverage and collaborate with our partners in industry and other agencies in the international arena to complement and build upon what we're doing within NASA. And we'd like to foster a national workforce for technology innovation by giving people within NASA and outside of NASA the opportunity to actually design, build, and test hardware so that they gain experience and can carry this into the next generation of people that support our space program. And we'd like to engage the public as much as possible through our demonstrations, getting them to participate in some of the exciting things that we plan to do. So our planned approach is to do some shorter duration demonstration projects. These would typically last between 2 to 4 years. And they would range from laboratory experiments to Earth-based field tests or even in-space flight experiments. But they're generally funded at about $100 million or less total life cycle cost. And they have very specific objectives, which is to demonstrate a new capability. At the same time, we want to provide a base of foundational technologies that would supply these demonstration projects so we can maintain the continuity of knowledge and capabilities within NASA. And we have had a technology program in exploration for the last 5 years. It's mainly been focused on supporting the Constellation program, but we'd like to build on all these previous technology investments and use that in our initial set of demonstration projects. Starting in FY2011, we're going to initiate 5 demonstration projects, and these will eventually lead to flight experiments of these new capabilities on other exploration missions in the flagship program or the robotic precursor program, or even on international missions around the 2015 timeframe. And one of our goals is to compete majority of the program funding because we believe that really drives innovation and helps to capture the really best ideas from both within NASA and from outside of NASA. And we're looking at ways to structure these competitions so that NASA and the external partners are not competing head-to-head against each other. So we're looking at separate competitions, intramural and extramural. And again, I just wanted to emphasize that we're trying to take advantage of the broad range of possible test opportunities on a lot of different types of platforms. Okay, this chart diagrams our relationships to other technology programs. The ETDD program is shown there in the center, and just below in the yellow bubble is the Human Exploration Framework Team. And again, they're studying future mission concepts, supplying us with technology, priorities, capability needs. We build proof of concept systems and feedback the feasibility of those concepts to the Human Exploration Framework Team. Our primary customers for these new capabilities are shown on the right-hand side. Up at the top, it's the flagship technology demonstrations, which you'll hear about soon. Again, we're building prototype systems, demonstrating them in a relevant environment, and then handing them off to the flagships program to demonstrate as part of a larger system in a spaceflight experiment. We're also like to fly some of the things I'll describe in a few minutes on exploration robotic precursor missions to the moon, to near-Earth objects, and to Mars. And we would like to utilize the International Space Station as a test bed, so you can see that over on the left-hand side. Some of these systems, such as life support systems, robotics, and propulsion, we could test on the International Space Station, so we're working closely with our Space Operations Mission Director to plan those activities. And then up at the top, you see the cross-cutting technologies that are being developed by the new Office of Chief Technologist, and they have a program called the Space Technology Program. And as those technologies mature, we will begin to infuse those into our missions by focusing them on exploration-specific applications. This program is really developing the really advanced concepts and lower TRL activities that cut across the whole agency, and then we would focus them on exploration-specific objectives. And then in the lower left, you see there are missions of opportunity. The Science Mission Director at NASA is flying experiments to Mars. We could take advantage of some of those missions to Mars to test exploration technologies like NCU Resource Utilization and others. And there are a number of international partners who are planning missions to the moon or near-Earth objects that we'd like to use as platforms to test our new technologies. You'll hear a lot more about the commercial crew development program later today, and that's trying to enable the ability to launch astronauts into low Earth orbit on commercial rockets. But our program is would like to address some of the longer range technology needs for that program. So if there are any providers of those vehicles who are interested in life support technologies or avionics or thermal protection system materials that could enable these activities, please come see us in our one-on-one meetings tomorrow. We'd be very interested in addressing some of those longer range needs for you. And then at the very bottom there on the right, we're working closely with the Human Research Program on the area of space radiation protection. The Human Research Program investigates the effects of space radiation on the human organism, and the Enabling Technology Development Program will be addressing the radiation shielding concepts and materials development. Okay, this is our proposed program structure. In the pink circles up at the top are our demonstration projects, and those have very specific objectives to demonstrate a key capability of exploration, and they typically last between 2 to 4 years. And then those projects would end, and we'd start another set of projects. So the initial set of projects involves in-situ resource utilization, high-power electric propulsion, autonomous precision landing, telerobotic operation, and fission power systems. And I'll describe those more in a few minutes. We'll start those in FY11, but we're also planning other demonstrations like in extravehicular activity, EVA technology, in radiation shielding, and in life support systems. Underlying these demonstration projects, you see in the blue bars there are foundational technology domains. These are 10 critical areas that we've identified that provide the long-range foundation for exploration activities, and they would supply technologies to the demonstration projects. The domains would take very low readiness level technologies and mature them into practical system applications, and we would then hand those off to the demonstration projects for validation. So the foundational domains are meant to continue year to year, and they provide the continuing base of knowledge and the core competencies in these critical areas within NASA. And you can see that each demonstration project may involve several foundational domains. For example, the high-power electric propulsion demonstration may draw upon electric thrusters from the advanced in-space propulsion domain, and it might draw upon solar or nuclear electric power systems from the high-efficiency space power systems domain. Okay, so now I'd like to describe the initial set of demonstration projects and how we came up with these. And we looked across a lot of the previous architectural studies, and there are a lot of common themes for the critical capabilities that are needed. So we looked at the design, the Mars Design Reference Architecture 5.0. We looked at the global point of departure lunar architecture that the international community has been working on for the past few years. We looked at what the Augustine Committee had proposed in their report, and the Human Exploration Framework team is going to fill in some of these gaps. But looking across that set, we identified things that we could do in the near term that build upon our current technology investments. So we wanted to have some quick successes, some near-term wins. And these projects would demonstrate major advances in capabilities within the next 5 years, making the first steps on our longer-range strategic technology roadmaps. And we set up these projects so that they will deliver their technology products in time to support the major mission milestones of the flagship's technology demonstration program and the exploration robotic precursor program around the 2015 timeframe. And assuming that we get the approval from Congress to initiate these programs in fiscal year 11, we start the programs and move out on their implementation as soon as we could. And we've tried to frame each of these programs around addressing a key question for exploration. So the first project I'd like to describe is involving NCU Resource Utilization, and it's trying to address the key question: how can we locate, access, and extract volatile resources on the moon? As you know, the Lunar Reconnaissance Orbiter and the LCROSS mission both have found strong evidence for water and other volatiles in the lunar polar regions. We'd like to take that to the next step, which is to provide the ground truth for these orbital measurements. And so the idea is to develop a small experiment that could fit on a lunar lander or rover that would prospect for ice and other volatiles in the polar regions. And the idea is to have some sort of subsurface sampling device, like a drill, that could bring up samples of the lunar regoliths from several meters below the surface. We'd heat it up in a small oven, drive off the entrained volatiles, and analyze that with a mass spectrometer or a gas chromatograph or other characterization instrument, and just determine the abundance of the resources that might be in the polar regions. And this is important because if we ever want to enable an exploration infrastructure that uses in-space refueling. It might be a lot easier to produce propellants on the moon instead of launching them from Earth, which is much more expensive. And ISRU can really reduce the amount of consumables like rocket propellants, water, and oxygen that we have to bring along with us from Earth for human exploration missions. The top-level requirements for this project are to locate the subsurface areas of elevated hydrogen concentration, to acquire samples from the subsurface, to analyze the samples, and if we, what we would like to do is actually demonstrate if we can extract the volatiles effectively from the regolith to show that they have potential for helping to supply our resources for future human missions. We want the experiment to be capable of flying on a variety of lunar lander platforms. As I mentioned, NASA's planning some lunar lander missions. The international partners are planning lunar lander missions. The Google Lunar X Prize is planning lunar lander missions. So there's a lot of opportunity to send payloads to the moon in the next few years, and we'd like to be able to fly on any of those missions that we're compatible with. We'd like to go to a polar location, and we have some initial targets for mass and power that are shown there. And I might add that we've been testing this prototype system in Hawaii in the last 2 years, working with the Canadian Space Agency. Okay, the next demonstration project involves high-power electric propulsion, and it's trying to address the key question: how can we reduce the travel time and cost for sending humans on deep space exploration missions? You'll see later today in the flagship technology demonstration program a large solar electric propulsion system that they would like to build and demonstrate. And the goal of this project is to provide the higher power electric thrusters that would be tested on a second generation version of that flagship solar electric propulsion mission. We'd like to develop high power electric thrusters that are scalable to the power levels we'll ultimately need for human missions. These are hundreds of kilowatts up to megawatts of power. And this is a ground test. We would integrate advanced electric thrusters with the power management system, the propellant feed system, and we test them in a vacuum chamber, qualifying them for spaceflight demonstration. And we're looking at ways that we could even use the space station as a platform for testing some of these new thrusters in orbit. The objectives are to focus on higher power thrusters, again in excess of 100 kilowatts, high specific impulse. You can see from 3,000 to 7,000 seconds. They must be scalable to power levels in excess of hundreds of kilowatts up to a megawatts, and operate continuously up to 3 years. And we'd really like to leverage existing high-power generation systems like advanced solar arrays or other concepts like nuclear fission power systems to supply the power needed for these high-energy propulsion systems. The next demonstration project involves autonomous precision landing, and its question that it's trying to address is how can we land autonomously, precisely, and safely on an extraterrestrial surface. And over the last few years, we've been developing sensors and algorithms that would allow a lander to the moon or to Mars or an asteroid to identify hazards on the surface, such as rocks or craters that are in the landing zone, and then maneuver the vehicle autonomously to avoid those objects and set down softly on the surface. Right now, when we send a mission to Mars, we can only come within tens of kilometers of the targeted landing site. With this technology, we are stepping that capability up several orders of magnitude. We want to land within 10 meters or less of a predefined target. So this is a major advance in capability. We're looking at flash LiDAR sensors to build up a three-dimensional image of the terrain. We're looking at optical imaging and comparing features on the surface with the database on board the lander of features to figure out where on the trajectory the lander vehicle is, and other methods to enable precision landing. What we'd like to do with this experiment is have a small lander vehicle that would take off vertically, fly up to about 1 kilometer. This is an Earth-based flight test. And then we would fly a simulated descent profile, and the autonomous landing system would control the vehicle, and it would set it down safely in the presence of big obstacles in the landing zone. We've done a lot of helicopter flight tests over the past few years on this technology, but those have been open loop tests. We've never closed the loop on the control system so that it can steer the vehicle in real time. So that's the objective. And we'd like to take advantage of some of the lander vehicles that have been developed by the Centennial Challenges prize competition competitors or others that might be out there. And our requirements are to be able to land in any location that's certified as feasible for landing. The vehicle must be capable of identifying the hazards in the landing zone and diverting in real time to avoid those. We want to be able to land in any lighting conditions, even if it's pitch dark. We want to be able to land autonomously, because that will enable us to supply cargo to future human missions in any conditions. We don't want to use any pre-in-place navigational aids or GPS. We want to just use natural features and figure out where we are relative to those features and land within 10 meters or less of a predefined target. And again, we'd like this system to be capable of flying on any mission of opportunity so that we can take advantage of some of these international missions or commercial missions or NASA missions to the moon that are planned around 2015. The next project involves controlling robots either on the ground or in space using teleoperation. We see this as a major capability for human missions to asteroids or to Mars. The idea is that in those future human missions, we'd have a crew in orbit before they land, controlling robots on the surface to set up equipment, to scout the area around the landing site. And the crew would be teleoperating these robots on the ground. So what we'd like to do to demonstrate that technology is have astronauts on board the International Space Station controlling a variety of robots in the desert. Every year we have a desert field test of some of our robots, but those are controlled either locally or remotely through the internet, but we've never actually controlled these robots from orbit. So that's one of the main objectives. The other objective is to have people on the ground controlling robots in orbit to assist humans as they assemble and maintain systems in space. We're planning to launch a human-like robot called Robonaut 2 on the last shuttle mission to the International Space Station, and we'd like to teleoperate that robot from the ground. Some of the top-level requirements for this demonstration are to remotely operate the robots both on the surface and in orbit. Using teleoperation, we want to quantify the benefits or the limitations of having humans and robots working together. We want to be able to control different types of robots and multiple robots at the same time. We might control robots on the ground at several locations around the globe at the same time from the International Space Station. And we would like to use the space station as the test bed for this. And then the final demonstration project is working on fission power systems technology. We know that we're going to need abundant supplies of power for human exploration, and in a lot of cases, if we're far from the sun, the only way to do that effectively is with nuclear energy. These could either be surface power systems, or they could be in-space power systems for nuclear electric propulsion vehicles. But the idea of this demonstration is to test the integrated power generation and thermal management system. This is a non-nuclear test because building a nuclear reactor is very expensive and requires a lot of safety protocols. We're trying to test all the non-nuclear components as an integrated system. So we simulate the reactor with electric heaters, but the heat from this simulated reactor would be used to run a heat engine like a Stirling converter, and that would generate electricity. We cool the simulated reactor with a liquid metal coolant loop or some other technology, and then reject the heat with these high temperature deployable radiators. This integrated system would be tested in a vacuum chamber on the ground, and it would show that we're ready for the next step, which is development of the reactor itself. So we're trying to target a 40 kilowatt fission power system. It must be capable of operating on the moon, on the Mars, or in deep space. It provides continuous power for up to 8 years. It has a low sensitivity to environmental conditions like temperature changes, dust, and the vacuum. And we want it to be self-regulating, operationally simple, so that we don't have to use a lot of human control. And it's fail-safe. And we want to validate some of the models we've developed for overall system performance. So those are our initial set of demonstration projects. They address the key areas of in-situ resource utilization, advanced in-space propulsion, autonomous systems, telerobotics, and power generation. So we think that's a good set. It looks like the dates up top are scrunched up a little bit, but the point of this chart is that the blue milestones for each of the demonstration projects would lead to inclusion of these capabilities in later exploration missions done by the flagship program or the robotic precursor program. And those are all targeted for about the 2015 or 2016 timeframe. Those are the green diamonds shown on the far right. So our demonstration project milestones are aligned and scheduled so that they feed into these future mission opportunities. Okay, on May 10th, we issued a request for information, and the purpose of this was to seek ideas that will help us formulate these initial demonstration projects and outline our acquisition strategy. So we're looking for ideas of demonstrations that could address the key questions that I posed earlier, technologies that would support these planned demonstration systems or test platforms. The major topic areas under the linear volatiles experiment are instruments to characterize and detect subsurface volatiles, or test chambers. We'd like to test this system on the ground in a dirty vacuum chamber. In other words, a vacuum chamber that simulates the space environment with lunar dust present, so we can see how it will work on the lunar surface. High power electric propulsion system, again looking at high power electric thrusters. For autonomous precision landing, we are looking for platforms, and the fission power system, we're looking for ideas to support that as well. So the responses are due on June 4th, and you can see the website there. And please come to our one-on-one meetings tomorrow to discuss your ideas. Now let me quickly describe the foundational technology domains. Again, these are a set of key capabilities that support critical exploration needs in the long term. They apply to a variety of applications such as the Moon, Lagrange points, near-Earth objects, and Mars missions. As an example, the foundational domains would support long-range capability needs for a NEO mission. So here's some of the things we need for a NEO mission: advanced in-space propulsion and electric propulsion systems to get the crew there quickly, robotic systems so that we could amplify human productivity, life support and habitation systems to allow the crew to live for long periods in deep space, and then EVA technology to allow the crew to work on low gravity surface environment as they're exploring the asteroid. Some of the key priorities in the near term for these areas I'll just highlight a few. In advanced in-space propulsion, we'd like to begin nuclear thermal propulsion foundational technology, so working on fuel elements and materials and concepts for nuclear thermal rockets. In the life support area, we'd like to emphasize ways to further the closure of the life support system, and by recycling water and air and waste. And you can see some of these priorities for the near term in these areas. So quickly, the acquisition strategy we have laid out. The RFI is the first step to help gather ideas to plan the demonstration projects. Once we formulate the projects, we'll issue some sort of competitive solicitation to select external team members for these projects. That might be an announcement of opportunity or a cooperative agreement notice. We are planning a broad agency announcement in the late summer, early fall timeframe to support the foundational technology domains, and these are soliciting long-range R&D projects that are led by principal investigators. And then as those technologies are matured, we'll down-select the most promising ones, and we'll focus those into exploration specific mission test beds, and we'll gather new technologies coming in from the Space Technology Program. So the next steps, our Glenn Research Center is leading the program formulation. Again, please talk to Tammy about that. We have formulation teams led by the NASA centers that have been established, working through the plans for the demonstration projects and the foundational domains. The RFI responses will be used to guide program formulation, and we are planning additional solicitations in the summer, an announcement of opportunity for our demonstration projects to select the external team members, and this broad agency announcement for the long-range research and development. And so to summarize, this program matures technologies to the point where they can be demonstrated in small ground or flight experiments. We then hand them off to other exploration missions for validation. We provide an infusion path for game-changing technologies coming from the Space Technology Program. We've outlined a set of 5 initial demonstration projects, and we've defined 10 foundational domains that develop the long-range exploration-specific technologies that feed the demonstration projects. So that's it for me. Do I have time for questions, or should I wait?
Take 1 or 2 quick questions if we have them.
Okay, sir.
Try again. Dave Aiken, University of Maryland. NASA's last technology program, which was terminated when Project Constellation came along, had specific elements focused at low and mid-level TRLs. This program seems to be strongly focused on flight programs, which is the highest TRL, the most expensive per program. Also with the restriction to ESMD technologies, that was that technology program was almost entirely in-house at NASA, which means you're flying NASA technologies. So do you think that this program, in a strategic sense, is really the optimal one for NASA in terms of bringing out technologies at all TRL levels and in terms of appropriate mix between NASA in-house and non-NASA sources for the technologies?
Yeah, we do. The way the program is structured, again, is it includes both the low TRL technologies in our foundational domains, and we are using broadly competed solicitations to gather the best ideas from outside of NASA to support the long-range low TRL technologies development. But we also have the mid-TRL demonstration projects to focus these longer-range technology developments on practical mission applications. And again, we're trying to compete at least 50% of our program funding. The key differences with this new program is we've built in competition, we've built in a way to maintain longer range base of foundational technologies, the low TRL technologies, and we have very specific demonstration projects that will focus these technologies on practical applications. So we think we've covered the waterfront with the whole range of technology readiness levels and involving outside participants.
Yeah, how do these overlay with the 5? And I think that was what you were just addressing in the different levels.
I think the best way to describe that, again, is back to this structure chart. But the 10 foundational domains underlie the demonstration projects. Demonstration projects come and go. They only last couple of years. They have very specific objectives, and then we start new demonstration projects as the need arises. But the foundational domains continue year to year, and their objective is to provide the foundational knowledge base in critical technology areas so that we're going to have a supply of new technologies to demonstrate. If we didn't have these foundational domains, we'd quickly run out of new technologies. So the domains mature the lower TRL technologies to the point where they can be integrated into representative systems, and then they're handed off to the demonstration projects for validation in a relevant ground or flight environment.
So the foundation technology domains are running in parallel with the demo projects?
That's correct.
Under the BAAs and the other activities?
Right, so the BAA supports the foundational domains, the RFI and the announcement of opportunity we plan to issue later this summer would support the demonstration projects. So there's two main parts to the program, and they're managed separately because they're different types of projects. The demonstration projects are managed more like a flight project, whereas the foundational domains are more like a portfolio of technologies that are matured.
And which final part of this is which set of these are under the $100 million max program?
Well, we haven't specified whether that is a demonstration project or a foundational domain. It depends on our relative priorities, but usually we don't want to go up that high. We want to try to be cost-effective and do as many smaller projects that involve ground-based experiments or small flight tests as possible. But that's sort of an upper limit. And
Okay, thank you.
okay, thank you.